Okay, so previously we discussed utilizing the pKa tables and tabulated pKa values to estimate and relate acid and base strength. What we're now going to do is we're going to take a qualitative perspective where we focus less on the hard numbers of pKa values and more on analyzing a structure to estimate relative acid and base strength. So let's first talk about the key features of organic acids. So organic acids are characterized by the presence of a positively polarized hydrogen atom. And in general, alcohols and carboxylic acids will lose a proton from their oxygen-hydrogen bond. So in both of these cases, we have a positively polarized hydrogen atom. Now, the carbon-hydrogen bonds adjacent to carbonyl functional groups can be dissociated to give a proton and a stabilized anion. Does everyone see how after the loss of this proton, our anion is stabilized via resonance? Does everyone see that in the following anion? This type of anion is also known as an enolate. Okay, so we've noticed that organic acids in general have a positively polarized hydrogen atom, and they generate anions that are either stabilized via resonance or the anion is placed on an electronegative atom, such as oxygen. Wonderful, okay? Let's look at the key features of organic Bronsted bases. Organic bases are characterized by the presence of an electronegative atom with a lone pair. And the basic lone pair can readily accept a proton to form a conjugate acid. So for example, an amine functionality, such as methylamine, for example, can react with an acid and in turn generate a conjugate acid and the conjugate base. Now, just to note, the pKa of this ammonium is around 9 to 11. If we try to do the same trick with methanol, we're going to run into a little bit of a problem. Because just as a refresher, what is the pKa value of a protonated alcohol roughly? What is the pKa value of a protonated alcohol? Looking at the pKa tables that I gave you in the notes, what is the pKa value? About negative 1.74. Okay. If we look at acetone, if you try to protonate acetone, whoops, there we go. Technically, this lone pair can function as a base. It doesn't function as a base very often. Because what is the pKa value of a protonated ketone? Well, let's look. If we go to a protonated ketone, what's the pKa value of a protonated ketone, roughly? Negative 7.3, exactly right. Perfect. So we've shown sample examples of how each of these organic bases can react, abstract a proton, and generate their conjugate acid. Does this make sense to everyone so far? Any questions so far? So let's keep going now. When we think about assessing Bronsted acid strength, so to assess the strength of a Bronsted acid, we look at the stability and basicity of the conjugate base. So a strong acid in general will produce a stable weak conjugate base. So for example, hydrochloric acid is such a strong acid because it generates a very stable chloride anion that is a very weak conjugate base. So the conjugate base is really key to understanding acid strength. Now, let's look at another example. Hydrocarbons are considered extremely weak acids, as if you break their carbon-hydrogen bond, you generate a carbon anion, which is unstable because it has a localized charge and it's on a not very electronegative atom. Does everyone see how this anion, is this anion stabilized by resonance or any other effects? Is this anion stabilized by resonance or any other effects? No, so it's a relatively unstable anion. And because this charge isn't stabilized, we have a highly basic anion that we're dealing with. Does this make sense to everyone so far? Okay, perfect. So, if you're comparing the strength of two Bronsted acids, we compare the stability and basicity of the conjugate base. So we look at each of the conjugate bases, and the more stable your conjugate base, the stronger your acid. So here are some factors affecting conjugate base and anion stability. The first of which is atom size and electronegativity. So we know that atomic radius increases as you move down a group and left across a period. So if we're thinking about the atomic radius increases going down into the left on your periodic table. Electronegativity increases as you move up a group and right across a period. So electronegativity you can draw with an arrow going up and to the right. Okay, so with these two factors, electronegativity and atomic radius in mind, we can observe the following major trends. First, anions are more stable on large electronegative atoms. So if we look at it from an electronegativity perspective, first and foremost, we see that as we go from carbon to nitrogen to oxygen to fluorine, as we have increasing electronegativity, what happens to our proton acidity? Does it increase or decrease? As we get more and more electronegative atoms bonded to our proton, does our acidity increase or decrease? Yeah, we have increasing acidity. Why? Because the carbon-centered anion is less stable than a nitrogen-centered anion, which is less stable than an oxygen-centered anion. Fluoride is our most stable anion. Does that make sense to everyone so far? Does that make sense? This logic can also be used to explain why a protonated alcohol is more acidic than a protonated amine. Because deprotonation generates a conjugate base where our oxygen is more readily able to stabilize our lone pair. And it's as a result, our conjugate base is less basic. Does that make sense? So the second major effect, which is far more important, is atomic size. Atomic size has a much larger effect on anion stability. Why? Well, you're delocalizing the anion charge over a larger region of space. The larger your atom, the more readily you can delocalize the charge across that larger atomic radius. So, for example, if we compare oxygen to sulfur, oxygen is smaller than sulfur, and because sulfur is larger, it's more readily able to stabilize your negative charge and stabilize the resulting conjugate base anion. And as a result, hydrogen sulfide is orders of magnitude more acidic because sulfur is a larger atom. So atom effects play a much bigger role than electronegativity. Because the larger your atom, the more readily you can stabilize and delocalize your negative charge. And we see this as well if we look at hydrofluoric, chloric, bromic, and hydroiodic acid. As we see, when we have a larger atom, we have a more acidic proton. Another argument that you could use is that the smaller your atom, the stronger your hydrogen-fluorine bond is going to be, and the harder it is to dissociate your bond. If we compare that to a hydrogen-iodine bond, where iodine is pretty massive, we have a weaker hydrogen-iodine bond, and as a result, we have a stronger acid. Both interpretations are usable for predicting acid strength. Does that make sense to everyone? Does this idea make sense to everyone so far? Perfect. So, I'd like you to tell me which of the following compounds is more acidic, A or B? Which one's more acidic, A or B? B, yep. Why? Oxygen is more electronegative than carbon. Yep, perfect. Classic atom effects. Let's look at another atom effect example. Okay, and I'd like you to tell me, so A, B, C, D, E, F. So let's look at this first example. Which proton is the most acidic, A, B, or C? Which proton is more acidic, A, B, or C? C, yep. And we have two reasons for that. One, we have atom effects. And two, we also have electronegativity. Remember, the atom effects are actually more important in this case because nitrogen's more electronegative, but sulfur is larger. So it's more readily able to stabilize the negative charge over a larger region of space, and the sulfur hydrogen bond is weaker than a nitrogen hydrogen bond. Does that make sense? Okay, so now looking at the second molecule, D, E, and F, which proton is the most acidic? Which proton is the most acidic among D, E, and F? F, yep. And this we can invoke electronegativity. Now, if we had to pick in both of these molecules, what is our most acidic proton among all of these protons? What is the most acidic proton overall? What is the most acidic proton in both of these molecules? C. Why? Sulfur is larger than oxygen, and we're more readily able to stabilize our negative charge as a result. Or you can say the sulfur hydrogen bond is weaker, so it's easier to dissociate the proton. Both arguments are reasonable. Does this make sense to everyone so far? Okay, perfect. So let's now take a look at the following molecule, and I'd like you to tell me which of the following protons is the most acidic, A, B, or C. And don't be shy to type in the chat. I see a lot of C's in the chat. Yep, exactly right. Selenium, it's a large atom. It's pretty electronegative. It wins out over carbon and nitrogen. Does this make sense to everyone? Perfect. So let's keep going. There's another effect that has a pretty pronounced role on conjugate base and anion stability, and that would be resonance. So anions are more stable if the charge and electron density can be delocalized over multiple atoms via resonance or conjugation. The more delocalized the charge, the more stable your anion. We can see this practically when we compare an alcohol to a carboxylic acid, because in our carboxylic acid, we have a resonance stabilized anion. And as a result, because our anion is more stable, we have a stronger acid for our carboxylic acid. Does that make sense to everyone? So let's take a moment and let's try to answer the question. Which of the following two protons, A or B, are more acidic? I wouldn't think of it as like the 1.5 bonds are going to be more acidic. It's more that when we make an anion, that anion is delocalized and stabilized via resonance. Does that make sense? Perfect. So let's take a look at this example, and I'd like you to tell me, A or B, which of these anions is more acidic? Which of these protons is more acidic? And in other words, which of these anions is more readily stabilized via resonance and other effects? I see a lot of A. Yep, that's exactly right. Why? If we generate this nitrogen-centered anion, we can delocalize our lone pair into oxygen and in turn stabilize our lone pair via resonance. Yeah. So we have a resonance stabilized anion for A. Does that make sense to everyone? Now, this is a fun example. A versus B. Which proton is more acidic? So a vinylic, and we call this proton an allylic proton. It's not an alkene proton. This proton is known as an allylic proton as it's adjacent to a double bond. Which of these protons is more acidic, A or B? And be really careful on this one and make sure you're thinking about your anions and your anion stability. Well, let's entertain the two possibilities. This is the anion formed from A. This is the anion formed from B. Which of these anions is stabilized via resonance, A or B? Which of these anions is more stable? Well, B, is it next to a double bond or is it on a double bond? So your logic is right, but which of these anions is actually able to participate in resonance delocalization, A or B? Yep, A is able to participate in resonance delocalization. It's stabilized and delocalized as a result. And in turn, that means the anion A is more stable, and as a result, the proton A is more acidic. So this is a case, where resonance effects play a really important role in the overall acidity of two protons. Does everyone understand why A is more acidic? If we deprotonate, if we break this carbon-hydrogen bond and generate an anion from proton A, we'll in turn generate an anion that can be delocalized and stabilized via resonance. As a result, A is a more stable anion, and as a result, proton A is more acidic. Does that make sense to everyone? Is everyone comfortable with this idea? Okay, let's look at the next example. I'd like you to tell me which of the following protons, A or B, is more acidic, and which of the protons, C or D, is more acidic. Let's take about 2 to 3 minutes to work on this example, and then we'll come together as a group to discuss. So don't be shy to message in the chat which of the two protons you think are most acidic. And when in doubt, make sure to draw out your anions and check to make sure which anion is more stabilized via resonance and conjugation. Let's try to get a few more responses in the chat, and then we'll discuss this example in about another minute. So we have some contention whether A or B is more acidic. So let's look at the anion generated from A. And let's look at the anion generated from B. And my question to you is, which of these anions is more stable? The anion generated from A or B? Which of these anions is more stable? What does everyone think? The anion generated from A, that's right, because this anion can participate in resonance delocalization. So as a result, we have a more stable anion, and as a result, proton A is more acidic. Does that logic make sense to everyone? Does this first part make sense? When in doubt, draw the anions. So looking at the second structure, so if we compare protons C and D, well, let's draw our anions. So the anion generated from C looks something like this. The anion generated from D looks something like this. And my question to all of you is, which of these two anions is more stable, C or D? Which of these anions is more stabilized via resonance? C, yep. So as a result, proton C would be more acidic. Does that make sense to everyone? Perfect, perfect. So let's keep going now and let's look at vitamin C. Vitamin C has a highly acidic proton with a pK around 4.2. I'd like you to identify the most acidic proton in vitamin C. So we have A, B, C, and D. We also have proton E and F. I'd like you to tell me what is the most acidic proton in vitamin C. And for this, you're really going to have to draw out your anions and check to see which anion is more stabilized via resonance effects. And we'll discuss this example in about 2 to 3 minutes. But please don't be shy to submit your proposed response in the chat for the most acidic proton. And my hint to you is you want to make sure you're drawing out your anions and seeing how can I delocalize my electron density. And we'll discuss this example in about another 1.5 to 2 minutes. And don't be shy to submit your proposed responses in the chat, and we'll discuss in about another 1.5 minutes. Let's try to see a few more responses in the chat, and really don't be shy if your responses differ from your classmates. And when you submit your response, don't be shy to also provide a reasoning. So we have a proposal for C. Would you like to elaborate on your explanation for C? Or why did you pick C? Okay. So let's try to have a logical framework utilizing our theory about resonance. So people are mentioning C reminds them of a previous example that we've done. So let's look at our anions for D and C. Does anyone have another proposal for the most acidic proton? So for D and C, the first thing that we're considering, we have atom effects. So oxygen is preferred, right? So we want to form an anion on oxygen. So let's look at the anion formed from D. One of your classmates invoked an argument on proximity. Well, proton D is close to our carbonyl. So it would experience stabilization from our carbonyl. That's known as an inductive argument, or an argument utilizing the chemical principle of induction. It's a reasonable first pass, for sure. Now, if we think about how we can delocalize our lone pair, we can delocalize our lone pair via resonance onto our adjacent carbon atom. Wonderful. Let's look at proton C. Let's look at proton C. Ironically enough, in a vitamin C example. So we have our anion, and in this case, we can delocalize our anion throughout our ring across 1, 2, 3, 4, 5 atoms. So which of these protons experiences a greater amount of stabilization via resonance delocalization? which of these anions is more stable? The anion formed from D or C? C, yep. So as a result, proton C is more acidic. Does that make sense to everyone? Does everyone understand why proton C and D are so acidic? So you really need to draw out your structures. We teach resonance structures because they're critical for your analysis of the relative stability of anions and other species. So even though proton D, we're closer to our carbonyl, it's not able to actually delocalize its electron density into the carbonyl via resonance. Does that make sense to everyone? So that's why this proton has a pKa around 4.2, which is 13 orders of magnitude. It's almost millions or billions of times more acidic than your normal alcohol proton with a pKa of around 17. That's a huge effect, thinking about the difference in pKa units. I'm really surprised that no one said E. Proton E is actually pretty acidic. Not substantially so, but it's not negligible. Yeah, the main thing about E is that the atom effects. It's on a carbon, and carbon-centered atoms, carbon-centered anions are generally less stable than oxygen-centered anions. Well, I mean, when you deprotonate it, you make an sp2 anion, right? Like if you deprotonated E, you'd get something like this. But the reason why E is not particularly acidic is just because you end up with anions centered on carbon. And even though this anion is resonance stabilized, the oxygen-centered anion is also resonance stabilized. And atom effects can play a pretty big role, right? Remember how we looked at a carbon-hydrogen pKa around 50, while an oxygen-hydrogen pKa is around 17. So atom effects can partially dominate our discussion compared to the resonance effects that we get by being able to delocalize our lone pair. Does that make sense to everyone? Perfect, perfect. So, I'd like you to tell me which of the following protons is more acidic. And this example really helps us highlight a point. When you're comparing proton acidity, make sure to consider the electronegativity of all atoms participating in resonance. And I'd like you to tell me which of the protons is more acidic, A or B. And not just which proton is more acidic, but why. So we have an argument that A is potentially more acidic. Okay. Now my question to all of you then is, what atoms are we delocalizing our charge across? Carbon atoms, right? So then, if we compare A and B, let's elaborate on that discussion. So let's look at the anion generated from A. Just looking at pKa values, we know this pKa is around 9 and this pKa is around 4. So our goal is to, now that we have that knowledge and we know these pKa values from our pKa table, let's try to explain why. Why is proton A less acidic? Well, if we have our anion, we are primarily delocalizing and distributing our charge onto carbon atoms. So we primarily have our anion delocalized on carbon atoms. Does everyone see that? Does everyone see how the anion ends up on a carbon atom? Now, if we compare that to B, where if we have the anions generated from B, we are delocalizing our lone pair electron density and our anion onto oxygen atoms. So in the second case for proton B, as we can see quite clearly in proton B for our anion is delocalized on oxygen atoms. So oxygen is more electronegative. Ergo, anions delocalized across oxygen atoms are more stable. So these electronegative atoms are more readily able to stabilize our negative charge. Does that make sense to everyone? Perfect. So let's keep going now. Now, the next effect we need to talk about are inductive effects. Induction, what is induction? Well, induction is this idea that electronegative atoms draw electron density in the molecule towards that atom. So electronegative atoms draw electron density from atoms bonded to that atom and the adjacent bonded atoms. So for example, these chlorines are really electronegative, so they're pulling on this hydrogen. This hydrogen, they're pulling on this carbon. This carbon in turn, then, because this carbon is electron deficient, this carbon acts like a more electronegative atom. And as a result, this carbon pulls on the adjacent carbon, which then behaves like a more electronegative atom, which pulls on the adjacent oxygen, which pulls electron density away from hydrogen. So in the end, electron density is quote unquote pulled from hydrogen. And we end up with a partial positive charge building up on our hydrogen atom. So the way that you can think of induction is the presence of electron withdrawing atoms in one region of the molecule draws electron density from adjacent regions of the molecule. Inductive electron withdrawing groups draw electron density away from the atoms attached to the acidic hydrogen. Does this idea of induction, where we're pulling our electron density towards our electronegative chlorine atoms and away from our acidic proton, does that make sense to everyone? Perfect. And we can see that it has a dramatic effect on pKa, where addition of electronegative chlorines on one region of our molecule results in a substantially more acidic proton. Now, another way to think about this is because your oxygen atom is more electron deficient from these inductive effects, because we have all these chlorines pulling our electron density towards our chlorine atoms, the anion generated by breaking the OH bond is substantially more stable as it's on a functionally more electron deficient and electronegative atom. So I like to think of induction as increasing the quote unquote effective electronegativity, how your atom actually behaves substantially. Why? This oxygen is more electron deficient than usual. And as a result, this oxygen can more readily stabilize your negative charge. Because although this negative charge isn't explicitly being delocalized via resonance, what we are seeing is that all of the atoms in our molecule are now behaving as if they're more electron deficient. And just like our example with acetic acid, electron deficient atoms and electronegative atoms can stabilize our negative charge more readily. Does that make sense? Does that idea make sense? So it's not direct resonance delocalization, but these inductive effects change the amount of electron density on the atoms in our molecule. They're more electron deficient, and as a result, they're more readily able to stabilize a negative charge. Any questions on induction? Any questions on inductive effects? Okay, let's keep going. So inductive effects, so that's a weird, let me provide a correction to that. Sometimes the structure editing program makes a mild error. So let me provide a correction to that. Here we go. This structure has a pK of around 0.77. So inductive effects depend on the electronegativity of the bonded atoms and the number of electronegative atoms. Does everyone see as we increase the number of chlorines, our pKa goes down correspondingly? Does everyone see how the more electron withdrawing groups we have, the lower our pKa? Does everyone see that trend? Additionally, the distance in terms of the number of bonds between the electronegative atom and the acidic proton directly impacts the pKa observed. The closer your electronegative atom is, the closer your chlorine atom is to your acidic proton, the greater the observed inductive effect. Does everyone see that as we move our electronegative atom farther away from our acidic proton, that our pKa increases? Does everyone see that effect? How inductive effects are based on proximity and distance. Does this make sense to everyone so far? Okay, so let's look at the following example. I'd like you to tell me which proton is more acidic, A or B? Which proton is more acidic, A or B? A, yep, it's closer to our electron withdrawing groups. Exactly right. Does that make sense to everyone? It looks like everyone's comfortable with this example. Let's keep going and let's do a few more examples. So which proton is more acidic, A or B? Which proton is more acidic? A, yep. It's closer to our electron withdrawing group. Yep, exactly right. Let's do a more interesting example. So one common role of chemists is to design and develop compounds with unique properties. I'd like you to consider the following compound, and I'd like you to label the most acidic proton and the second most acidic proton. And then I'd like you to try and draw a constitutional isomer of this compound that is slightly more acidic. Okay, we're starting to add some complexity here. So let's take about 4 to 5 minutes to work on this example, and I'd like to see an annotated structure for part B shared by at least one student in this session. And we'll discuss this example momentarily. So let's spend about 4 to 5 minutes on this example, and don't be shy to share your proposed responses verbally or in the chat. Let's try to see some responses in the chat. Which protons are the most acidic, and what would a sample constitutional isomer that is more acidic be? So don't be shy to break out the annotate tool, and we'll be happy to discuss this example in about another 2 to 3 minutes. And if you have any questions, don't be shy to ask them in the chat or verbally. So, looking at our proposals, let's label some protons. So A, B, C, or D. Which proton is the most acidic proton? Which proton is the most acidic proton? Would anyone else like to chime in with their proposal? Let's try to get a few proposals in the chat for the most acidic and second most acidic proton. Let's try to see what the class thinks overall on this example, and then we'll be able to discuss once we've had all this information compiled. So one of your classmates is suggesting that proton C is the most acidic. Does anyone have another proposal? So we have some assignments that A is the most acidic and B is the second most acidic. Okay. Does anyone have another proposal that we'd like to consider? And really don't be shy to share your response. Even if it's different from your classmates, the responses are very valuable for our discussion. Does anyone have another response for the most and second most acidic proton for this molecule? Let's try to get one more response in the chat so that way we have a pool of responses to go off of. Does anyone have another suggestion? Really don't be shy to share. Does anyone have any other suggestion for the most acidic proton in this molecule? Okay, so let's discuss now. So we have another proposal that B is the most acidic. Okay, so let's discuss and let's use our criteria. So thinking about our criteria, if we consider atom effects, which atom can more readily stabilize a negative charge? Oxygen or carbon? Which atom can more readily stabilize a negative charge? Oxygen, yep. So it looks like A is going to be winning out in atom effects. Next, we look at resonance. Okay, and in terms of resonance effects, so we see the anion generated from A can be delocalized. Let's look at B for a moment. If we make an anion from B, my question to you is, can we delocalize our anion generated from proton B via resonance? Just like was proposed by one of the students in the chat, is proton B relatively acidic as a result of this stabilization of our anion? Can we stabilize the anion generated from B via resonance? Yes, we can clearly see we can delocalize this lone pair into our carbonyl functionality. So proton B being the next most acidic seems reasonable. Looking at proton C, we have this anion that's on a carbon. Is it very favorable to have a carbon-centered anion? Not really. And is this carbon-centered anion resonance stabilized like proton B? Is this anion resonance stabilized? No. So it's going to be pretty low on our list in terms of acidity. Another thing I want you to keep in mind, this carboxylic acid, this entire carboxylic acid is electron withdrawing. It does impose an inductive effect. right? Because we have electronegative atoms bonded together, and these oxygens are going to pull electron density towards themselves via induction, right? Perfect. So my question to all of you is, if I want a more acidic compound, and I have 2 chlorines to work with, how can I get a more acidic compound? How do I increase the acidity of proton A? What can I do? What can I do to increase the acidity of proton A? What tricks do I have at my disposal? Keeping in mind, I have to have the same formula because I want to draw a constitutional isomer. What's one trick that I can do to increase this proton acidity? We have a proposal to break the double bond. Okay, so let's entertain this structure here. Let's entertain this structure here. Are you referring to something like this? Okay. Now, what is the typical pKa of an alcohol? What is the typical pKa of an alcohol? 17. So have we beaten the pKa of a carboxylic acid, which is around 4? We weakened it. It's good that we recognize that. Okay, so if we want to keep our carboxylic acid, but we can play around with this remaining chain, what can we do for this remaining chain to increase its acidity? Let's see. For an aromatic, we don't have enough double bonds in our original structure to draw a constitutional isomer that's aromatic. But that's a good idea. That's a good idea. An aromatic, introducing an aryl ring would stabilize our anion. But let's focus more on these chlorines here. Is there a way for me to increase my inductive effects and increase my inductive effects on this proton? Is there a way for me to observe a stronger inductive effect by moving these chlorines around? I can move the middle chlorine to the right end. Okay, let's entertain that possibility. We're on the right track. We're on the right track. So our other proposal is we still have our carboxylic acid, but we put both of our chlorines on the right-hand side. Would this be a more or less acidic proton if we move our inductive withdrawing group away? So if we move our chlorine away, this compound will actually be less acidic because inductive effects decrease with distance. We have another proposal that we move our chlorine closer. So what do we think about this one? What do we think about this constitutional isomer? Would we observe a more acidic proton because we observe greater inductive effects? What do we think from this proposal? What do we think about this compound here? Yep. So for this compound, we've moved our chlorine closer. We have larger inductive effects. And in turn, that leads to a more acidic proton. Does this logic make sense to everyone? Does everyone see the connection between constitutional isomers and designing structures and drawing structures with the desired properties? This type of question will show up on your exam. I will give you one structure and ask you to draw a constitutional isomer with a certain desired property, such as pKa, bond length, or bond strength. Does this example make sense now? Now, it's really important for these kinds of problems that you don't just, you draw out your reasonable proposals, but your goal shouldn't just be draw everything and then sort it out. You should draw your structures with a purpose and draw your structures with the chemical theory in mind. Otherwise, you're going to be sitting there for minutes at a time drawing 10 structures that may not get you closer to the goal. Does that make sense to everyone? But the ideas I saw in the chat were really good. They were on the right track and they were based on the chemical theory. So that's very encouraging to see. So we've actually addressed this example when we were asked to draw a constitutional isomer of the compound that's less acidic. We actually already did that. The first example would be this diol compound. That's actually a pretty creative example and pretty creative response. The other, slightly more straightforward and equally valid response would be to put both of the chlorines as far away from our acidic proton as possible. And both of these compounds will be less acidic. Does that make sense to everyone? Does that make sense to everyone? Okay, so let's keep going. And which of these constitutional isomers would be significantly less acidic? When working through this example, did we draw a constitutional isomer that's way less acidic? So if we label our isomers A and B, which isomer is way less acidic? Which isomer is substantially less acidic than our original structure? Which one? A, exactly right. It's really funny to see how the class is almost preemptively answered my follow-up questions for this problem. It's good to see. The reason why this is substantially less acidic, alcohols have a pK of around 17, a carboxylic acid has a pK of around 4. Does that make sense to everyone? Practically, if you've ever handled like chlorinated or dichloro or trichloroacetic acid, you'll know that these inductive effects can really add up. Acetic acid doesn't really cause major burns, while trichloroacetic acid will actually eat through most common needles that you use for transferring materials. And it produces pretty nasty burns. So the addition of electron withdrawing groups can have a pretty dramatic effect on acidity. Now, there's another effect that I'd like us to consider, which are orbital effects. Orbital effects can help us rationalize the difference in acidity between an alkane, alkene, and alkyne proton. So we know that anions are more stable if the electrons are placed in a lower energy orbital, right? And we know lower energy hybrid orbitals have more s character, right? So the sp orbital is the lowest in energy, the sp3d2 orbital is the highest in energy, in general. Now, because of that, in terms of anion stability, anions in an sp orbital would be more stable, right? Does that make sense to everyone? Lower energy orbital, more stable anion. Does that make sense? So then, if we look at an example like so, where we have proton A and B, what is the hybridization of the carbon that these protons are attached to? What is the hybridization of the carbon that these protons are attached to? So for proton A, what carbon is it attached to? An sp2, yep. And for proton B, what's the hybridization? sp. So then, which anion will be more stable, and in turn, which proton will be more acidic? The sp2 proton or the sp proton? Which proton's more acidic? We just said that anions are more stable in sp orbitals compared to sp2 and sp3 orbitals, right? So then, a more stable anion results in a more acidic proton, and since B, the proton is attached to an sp carbon, proton B will be more acidic. The reason for that is that if we think about an sp orbital is closer to the nucleus, and in turn, we have a more stable anion. If we compare that to an sp2 orbital, we have a higher energy orbital, and as a result, we have a less stable anion. Does this example make sense to everyone? Does everyone understand why proton B is more acidic? Okay, perfect. Now let's take a look. So let's rank these protons, A, B, and C. Let's rank these protons in order of increasing acidity. What's our most acidic proton in this molecule? A, B, or C? A, exactly right. So A is the most acidic. And now if we compare B and C, which proton is more acidic, B or C? Or are they the same? Which proton's more acidic, B or C? Proton B is more acidic. And why is that? This proton is known, I guess you can call it, this one's like pseudo-vinylic, as it's not directly adjacent to an alkene. And the reason for that is if we generate the anion from B, we can delocalize it via resonance. This anion is partially stabilized via resonance. It's not a huge effect, but B is more acidic than C. So as we notice, a lot of these effects play a role in determining the overall acidity of each proton. And it's very hard to separate these effects out, as often each of these effects come together to influence the overall acidity. Hybridization plays a bigger role than resonance effects in most cases. Does this example make sense to everyone? Perfect. So let's keep going now. So another effect that influences conjugate base and anion stability is known as solvation. we've been drawing all of these molecules, neglecting the solvent. And when you think about it, so if you have your reaction, for every molecule or so of actual reactant, we have thousands to hundreds of thousands, if not millions of more molecules of solvent. And the solvent doesn't just sit around innocuously. The solvent plays a really critical role in the stability and reactivity of species in solution. The solvent can't be neglected here. So the solvent can stabilize the anionic conjugate base through ion dipole or dipole-dipole interactions, right? So in general, alcohols and other acidic protons on more substituted carbons are less acidic as their conjugate base experiences less stabilizing interaction with the solvent. Now, why is that? Why is that? Well, if we think about our solvent, if we have our solvent, so let's pretend our solvent is like an alcohol, the less substitution we have, the easier it is to surround our anion with solvent. However, when we start to build up increasing steric bulk, we have more substituents on our adjacent carbon. In turn, this bulky substituent prevents the solvent from surrounding and stabilizing our anion. Does that make sense to everyone? The more substituents we have, the more bulk we have adjacent to our acidic proton, the harder it is for our solvent to interact with our acidic proton and to stabilize our conjugate base anion. That's why as we go from a primary to a secondary to a tertiary alcohol, as we have more substituents adjacent to our acidic proton, the less acidic that proton becomes. So just to get you used to the primary, secondary, and tertiary notation, a primary carbon has one carbon substituent attached. A secondary carbon has two carbon substituents attached. A tertiary carbon has three carbon substituents attached. And we call our alcohols primary, secondary, or tertiary. A primary alcohol has an alcohol attached to a primary carbon. A secondary alcohol has our alcohol attached to a secondary carbon. A tertiary alcohol, our alcohol is attached to a tertiary carbon. Does everyone see how we go from a primary, secondary to a tertiary alcohol? We have more bulk on our adjacent carbon. It's harder for our solvent to interact with and stabilize our conjugate base. Does that make sense? Does this idea make sense? Any questions on solvation effects? They're relatively minor, but just because they're minor doesn't mean they can't make a difference. So the more substituted the carbon the alcohol or XH bond is attached to, the more difficult it is for the solvent to interact with and stabilize the conjugate base. So, for example, if we have a tertiary carbon adjacent to our carboxylic acid compared to a primary carbon, which of these carboxylic acids would be more acidic? The species on the right would be more acidic. And the reason for that is because it's easier when we generate our anion, it's easier for our solvent, I'll abbreviate that with S, it's easier for our solvent to interact with and stabilize our anion. Well, if we have this giant bulky substituent, it's harder for our solvent to interact with and stabilize our anion. We can get less solvent molecules stabilizing our anion. Is everyone comfortable with this idea? Is everyone comfortable with this example? Does this concept make sense? Perfect. So let's keep going now, and let's identify. Let's keep going and let's pull up the next set of examples. One moment. So let's talk about factors affecting acidity, and let's talk about inductive and resonance effects together. So substituents, so different functional groups can exert both inductive and resonance effects. And we call a resonance donor a substituent that donates electron density via resonance. So for example, this oxygen substituent would be a resonance donor, as it is able to push its electron density into and donate electron density into our carbonyl functionality. And if we look at the pKa of this molecule, which is representing an ester functional group, esters have a pKa of around 30. If we compare that to just an aldehyde, for example, aldehydes have a pKa of around 20 to 22, closer to 20 actually. The main distinction between these two molecules is that your resonance donor in general decreases the acidity of adjacent protons as they donate electron density to conjugated atoms. So, yes, ketones are more stable than aldehydes, but they're less acidic, and we'll talk about why that is in a moment. So some common resonance donors that you need to be familiar with, are your amines and alcohols, your ethers, your amides and esters, and in terms of your weak donors, it primarily cuts off here. So resonance donors will destabilize anions that are conjugated via resonance, leading to a less acidic proton. So unpacking this ketone example, so we're comparing an ester this time to a ketone. Suppose we generated an anion here. Now, one thing that we can see is that our oxygen is donating electron density via resonance. Right? We're pushing electron density into our ketone functionality. So then, if we try to delocalize our electron density into the ketone via resonance, what we end up observing is that although we can draw a resonance structure, we still have this adjacent resonance donor that is kicking electron density in, and this donation destabilizes our anion. Does everyone see how this resonance donation effect is pushing more electron density into our ester carbonyl functionality, and in turn it's destabilizing the anion that we are delocalizing via resonance? Does that make sense to everyone? Anions do not like when you're pushing extra electron density into them. So when you have a resonance donor, it destabilizes any anion that is conjugated to it via resonance. If we compare that to our ketone functionality, we are able to generate an anion, and that anion, it does not experience destabilization from resonance donation. So we can engage in the typical resonance delocalization that we've seen for ketones and other carbonyl functionalities. Does this example make sense to everyone? Does everyone see how resonance donors can destabilize our anion? Any questions on this idea? Okay, so let's keep going now. So resonance acceptors. So resonance acceptors are substituents that accept electron density via resonance to conjugated atoms. So this nitro group is an example of a resonance acceptor. What do I mean by that? Well, if we generate our anion, if we generate an anion of the following molecule, this nitro group, even though it's all the way on the other side of this molecule, is going to have a pretty dramatic effect on stabilizing this anion. Now note, this isn't a direct effect. It isn't direct delocalization of this anion. However, if we draw a resonance structure for this molecule, we can begin to notice something a little bit interesting. So if we delocalize some of our electron density into our nitro group, we can draw the following resonance structure. And as we can see, this nitro group via resonance is pulling electron density towards it. Does everyone see how we're able to distribute our positive charge? We're able to distribute this electron deficient character to this adjacent carbon. And as a result, this resonance withdrawing effect can in turn stabilize our anion. almost via a pseudo-inductive effect in a way. So essentially, the nitro group by resonance is pulling electron density from our aromatic ring towards the nitro group. As a result, we end up with a large amount of electron deficient character on the atoms directly adjacent to our anion, and in turn, this electron deficient carbon can help stabilize our anion via almost like an inductive effect. Does that make sense to everyone? So you can see resonance effects without being able to necessarily delocalize your lone pair into the adjacent atom. Merely by proximity, some groups draw electron density towards themselves via resonance and inductive effects for that matter, and in turn, they stabilize anions on adjacent and conjugated atoms. Does that make sense to everyone? Does this idea make sense? So, strong acceptors would be nitrile, sulfate, nitro groups, while weak acceptors are aldehydes, carboxylic acids, ketones, esters, and amines. Resonance acceptors stabilize anions that are conjugated via resonance, leading to a more acidic proton. To showcase a more direct example, if we look at phenol, para-nitrophenol, these positions are known as ortho, meta, and para, or O, M, and P. Whoops. And the placement of your withdrawing group can directly impact the effect of resonance acceptors and resonance withdrawing groups on acid strength. So for example, let's just look at the para example for now. If we compare this para-nitro compound to just normal phenol, this para-nitro compound is substantially more acidic. And the reason for that is if we look at the anion that we would generate, this anion can be directly delocalized via resonance into our nitro group. And as a result, our anion is heavily stabilized, not just via delocalization, but it's delocalized onto very electronegative atoms. Does that make sense to everyone? Does everyone see how this nitro group can readily stabilize our anion? Now, resonance effects are more pronounced when you can directly delocalize your anion into the resonance withdrawing group. So let's keep going now. And let's talk a little bit about inductive effects and how inductive effects can play a role in relative anion stability. So as we talked about previously, electronegative atoms draw electron density from adjacent atoms and adjacent regions of the molecule, stabilizing your anions and increasing acidity. That's why your acyl chlorides are more acidic. because we have an inductive effect from the withdrawing chlorine. Now, as a corollary to these inductive effects, we can also say that less electronegative atoms donate electron density to adjacent atoms, and they destabilize anions, leading to a less acidic proton. So this carbon is donating electron density into our adjacent atoms. So this carbon can be thought of as an inductive donor. And in turn, if we generate an anion from this molecule, this anion is destabilized as a result of this inductive donation. Hydrogen being a less effective donor. So hydrogen is a less effective donor. And as a result, our anion is less destabilized, our anion is more stable, and as a result, the proton is more acidic. Does that make sense to everyone? The more attached carbons we have, the greater the amount of electron density we have that is being donated into adjacent atoms. Let's look at another example. Remember how we used solvation as a partial justification for the difference between a secondary and a tertiary alcohol? Well, if we compare, let me put in this tertiary. So looking at our tertiary versus a secondary alcohol, the tertiary alcohol, we have more carbon substituents, so we have a greater amount of donation of electron density. And because our molecule overall is more electron rich, generating an anion is less favorable. So that's another explanation outside of the solvation argument. Does that make sense? Perfect. So, one thing to keep in mind is that inductive and resonance effects must be considered together as a group. So as we see, these are the common pKa's for our protons adjacent to a carbonyl functionality. We can rationalize the first two pKa values by noting that nitrogen and oxygen are resonance donors. Nitrogen is a more effective donor than oxygen. So in turn, nitrogen destabilizes the anion more readily, resulting in a larger pKa value. Does that make sense? Does that make sense? The next two we can rationalize using inductive effects. Chlorine is inductive withdrawing, carbon is an inductive donor. Does this make sense to everyone? Does this next argument make sense? And in the last case, we can invoke our resonance argument, where we have a resonance withdrawing group that is very readily able to stabilize our anion. Also, this nitro group is inductive withdrawing. So two effects add together to lead to quite the acidic proton. So just by making small changes into our structure, we have changes in pKa of about 21 orders of magnitude. Does that make sense to everyone? Does this chart make sense? Are you able to explain? Are you able to explain the observed trends for these structures? Perfect. So let's talk about this with a little more nuance. So in this example, although oxygen is more electronegative, right? This oxygen is inductive withdrawing. Note that the oxygen is also a resonance donor. And this donor effect wins out over the inductive effect. And that's why this ester proton is less acidic. So in general, resonance donation effects will trump inductive effects for conjugated atoms. And that's in general, because as we see, we observe the same effect when we have an adjacent nitrogen group. Pretty cool, right? Now, we can unpack this a little bit and we can rationalize the exact same trend for nitrogen, where nitrogen is also a donor via resonance. Now, if you're asking, wait, doesn't chlorine do the same thing? Well, chlorine in this case is inductive withdrawing. And if we think about our resonance structures for chlorine, the relative amount of donation, is it going to be major or minor when we have a resonance structure that looks like this for our donor structure? The donation is going to be minor because chlorine really doesn't want to give up its electron density. It really doesn't want to have this resonance structure as a major contributor. So chlorine is not very effective at donating its electron density via resonance. It's much more effective as an inductive withdrawing group. And that's because this resonance structure is a minor contributor. Well, if you compare an amine, the amine resonance structure where we have donation of our electron density, this structure is relatively major because nitrogen can actually accommodate donating electron density via resonance and adopting and holding a positive charge, while chlorine cannot as effectively accommodate a positive charge. Chlorine's way more electronegative. Does that example make sense? So we have this push and pull dynamic between resonance effects and inductive effects. And the relative impact of resonance effects depends on the contribution of that resonance structure. For esters and amides, donation of electron density by our nitrogen or oxygen atom via resonance is significant because our resonance structures that we draw are relatively major. While for chlorine, it would much rather function as an inductive withdrawing group because the resonance donor, the contribution of this donor structure, quote unquote, is relatively minor. Does that make sense to everyone? So this is a good place to wrap up our supplemental lecture in lab. So I'll pause the recording at this time.